So, good morning, good afternoon, good evening, ladies and gentlemen, depending on where you are in the world. My name is David Crouch. I'm the section chair of the European section of the International Society for Respiratory Protection. And it's my great pleasure to introduce you to today's webinar on radiological hazards. So in terms of today's webinar agenda, I'm going to give you a brief introduction to who ISRP is. And then it's a great pleasure to introduce our three keynote speakers for today. Chris Jones from the Atomic Weapons Establishment, Peter Hillier from National Nuclear Labs, and last but not least, Paul Cooper, again from the Atomic Weapons Establishment in the UK. So without further ado, I will move on to the webinar, but a bit of background information on ISRP. So as I mentioned previously, we are the International Society for Respiratory Protection. We are a non-profit organization whose charter is to provide education and information to anyone involved in respiratory protection. We have 6 sections. Today's event is being put on by the European section, but we also have colleagues in Americas, Australasia, Japan, Korea, and Greater China. And the objectives of the society are to enhance ultimately health and safety of people involved in the use and requirement for respiratory protection devices. So whether that's through the encouragement and development of society standards and best practices for the development, implementation, and administration of respiratory protection programs, but also to promote research and evaluation into new forms of respiratory protection and technology involved in respiratory protection. And a key part of our educational program, which is what today is about, is the encouragement of exchange of information amongst not only industry, but governments, labor organizations, academia, manufacturers, and any other professional organizations involved. So as part of our education program, the webinar series that we've put on this year is introduce the audience to a range of respiratory protection backgrounds and requirements and how they can be used in response to mitigating against airborne hazards, whether that be radiological, particulate, or chemical, just as examples. So at the end of each webinar, the attendees will be able to appreciate the types and risks involved in airborne pollution and the pathways and symptoms if they're not mitigated, and then to look at different types of respiratory protection responses and types of equipment that can be used. So in terms of the webinars we've given today, today's is the 6th of this year's series. All the previous ones that we've run throughout the year, whether that be face coverings versus respiratory protection devices or confined space, can all be found on our YouTube channel. And these slides will be available to the audience on the ISRP portal afterwards. So that brings us to today's webinar on radiological hazards. So to set the scene, it's my great pleasure to introduce Chris Jones from the Atomic Weapons Establishment, who is going to give a background presentation on the basics of radiological hazards. So Chris is the current corporate radiation protection advisor for the Atomic Weapons Establishment. So Chris has got a background in physics. He was a former teacher prior to joining AWE, where he's been there since 2009. And Chris now heads up the Atomic Weapons Establishment's RPA body of more than 25 radiation protection professionals. And with that, Chris, it's a great pleasure to offer the floor for your presentation.
Perfect. Thank you very much. David, do you hear me?
Yes.
Lovely. And hopefully your presentation is coming up. Do you see that?
Yep, that's come through.
Fantastic, lovely. Yeah, right, good afternoon, morning, evening, everybody. Great pleasure to be here. Thank Thank you for that very nice introduction, David. I'm Chris Jones from AWE, as David just said. I'd also like to just flag up in the bottom corner there of my slides the Society of Radiological Protection, which is the UK professional society for radiation protection professionals. So I'm kind of speaking to you today on behalf of both those organisations. And yeah, very pleased to an introduction to the radiological hazards. This is very much a sort of hopefully a sort of broad introduction to the topic that will then allow those coming after me to give you some more specifics in their respective areas. So what I was going to speak about for about half an hour is a bit about what ionizing radiation is, where it comes from, a bit about why we're worried about it from a health protection point of view. Why do we have radiation protection professionals at all? Some bits about their routes of exposure, which then leads on to the considerations about sort of respiratory protection equipment. So, let's start. What is ionizing radiation? So I always think it's quite a nice idea to break that down into sort of the two separate words. So first of all, what is radiation? So radiation is anything that transmits energy away from a source. So I've got a few pictures here. All these things emit radiation of some form. So you've got speakers emit sound radiation, if you like. So the speaker takes the energy from the hi-fi or whatever's powering it, and transmits sound energy through the air to your ears. A light bulb emits light energy, light radiation. Mobile phone emits sort of radio wave, microwave type radiation to obviously transmit to the receiving antenna. And a radiator, as in a household central heating radiator, emits heat radiation, hence the name. So radiation. You can kind of have debates about convection and various stuff going on as well. But the point being that radiation is a whole load of different things, where all you're doing in every single case is transmitting energy away from a source towards some kind of receiver. Okay, so what's ionizing? So ionizing is a very specific process by which atoms become charged. So whereas all of those things above are radiation, none of them are ionizing radiation. Ionizing radiation has the potential to take a nice, stable, normal atom and dislodge, knock off one or more of the electrons which are orbiting around in the electron shells around that central nucleus. So ionization, we're taking a nice normal atom and turning it into an ion, a charged atom. Now, what's the big deal? Okay, we've knocked an electron off. Well, the problem is that that's fine when it's just one atom like that, but those electrons are what stick together atoms. If you're forming molecules where you're sticking atoms together, those electrons are the glue that stick it together. And so if we're building big complex molecules, like, for example, DNA, then the bonds that link all of those millions of atoms together in a DNA molecule are those electrons. And if I come along and start knocking electrons off, it's a bit like coming on pesters and cutting through the chemical bonds. And when that is something as complex and as important that it is all correctly sequenced as something like DNA, that's obviously going to start being a problem. So lots of things in the world emit radiation. Most of them are completely harmless to humans, but ionizing radiation is a very particular class of radiation that is harmful, which is the focus of what we're talking about today. Okay. So where does ionizing radiation come from? Well, there's two main sources. So the first one is radioactive material. So these are things everyone classically thinks of when you think of radioactive material. Sources, radioactive sources. The metal disc there being held by the two hands is a disc of uranium. And then up in the barrels, we've got lots and lots of drums of radioactive waste. So all the sort of classic things people think of when you mention radioactive material. And what unites all of those things is that they contain atoms which are, and specifically nuclei of those atoms, which are unstable. And so over time, the atoms and their nuclei decay, they fall apart to try and reach a more stable state. And when they fall apart, they emit this ionizing radiation we were just talking about. It's worth remembering, though, that radioactive material isn't just things that is created in the nuclear industry and in science labs. Naturally occurring ionizing radiation, naturally occurring radioactive material is all around us. So food like bananas have quite a high amount of radioactive material. Naturally occurring potassium-40 is radioactive. It will go through that decay, emitting radiation like we just talked about. But obviously completely naturally occurring and one of countless examples of that kind of thing. So ionizing radiation, radioactive materials isn't just about man-made artificial radioactive material sources. So that material emits ionizing radiation, as I just said, and there are 5 main types of ionizing radiation that we normally talk about. So they're alpha, beta, gamma, X-ray, and neutron. I'll go into them in a bit more detail in a second, but radioactive material essentially can emit all of those different types depending on the exact nature of the material. The other place we can get ionizing radiation from is some kind of electrical generating equipment. So your most classic example is something like an X-ray tube, an X-ray machine. So that there is just a very simple schematic of a basic X-ray tube. But the point is, in this case, that we have to apply an electrical voltage across it to get that radiation out. So whereas with the radioactive material, that radioactive material is always radioactive. We can't turn it on and off. It is always going to be emitting that ionizing radiation until all of the radioactive atoms have decayed away until none of them are left. Whereas with the electrical equipment, as soon as we remove the power source, so we unplug the battery or turn it off of the mains, then we lose that radiation being emitted from it. So from that point of view, it's a lot easier to deal with. The most sort of common type of radiation that's emitted by that type of equipment is X-rays. So obviously commonly in hospitals, medical settings, industrial radiography, commonly use X-rays. But you can get electrical equipment that produces almost any type of ionizing radiation. So all 5 types can come from either radioactive material or from electrical generating equipment. Once they've been produced, you would be hard pressed to tell the difference. A beta particle coming from radioactive material is the same as a beta particle coming from electrical equipment. Okay. So just very briefly going over those 5 types in a tiny bit more detail. What unites them all is that they all can cause that ionization, but because of their different masses and because of how they interact with other molecules and materials, they have quite different ranges. So you can see that an alpha particle can only travel a couple of centimeters in air, whereas gammas, X-rays, neutrons can travel hundreds, if not thousands of meters. Considerably further. And beta sort of sits there in the middle. And that also translates then to what happens inside the body. So if that radioactive, if the radiation is traveling within the human body, an alpha particle can probably only travel the range of about 3 human cells before it loses all its energy and is completely absorbed. Whereas beta particles, you're looking at more like tens to hundreds of cells. And with gammas and X-rays, it could be a number of centimeters between the interactions and causing ionization. Now, the impact of that is that an alpha particle and a gamma ray giving the same amount of energy into the human body will cause very different types of damage. An alpha particle is going to cluster all of that damage and all of the energy deposition into just a very small number of cells. So it will cause huge amounts of damage to just 2 or 3 cells. Whereas a gamma ray may cause 1 bit of damage to one cell, and then a few centimeters later, 1 bit of damage to another cell, and go on like that until it comes out the body on the other side. So it's overall the same amount of energy might be deposited, but the amount of damage per cell is quite different, which then obviously has a knock-on effect to how the health effect it causes. The other thing that's worth flagging up is what they can be stopped by. So if we're trying to shield those types of radiation reaching the body, then the things we're classically looking at, so just something very thin for alpha, some paper, dead layers of skin is sufficient. Beta, you need something a bit thicker, so a few millimeters of aluminium or perspex, still a fairly low density material, but you need a bit more of it than alpha. And then by the time you're up in gammas and X-rays, you're looking at sort of thick, sort of several centimeters of lead, potentially several meters of concrete in order to shield it. Okay. So we talked a minute ago about the ionization being caused in the body. In terms of the actual health effect that causes, it's worth considering that there's essentially three things that can happen when the radioactive material, when the ionizing radiation causes the ionization in the body. So the first thing is, fortunately, 99.99% of the time, your body repairs that damage perfectly. Your body has got amazing mechanisms that is able to repair the damage to the DNA and gets it right almost all of the time, which is really good, and thankfully means that despite all of that background radiation and all the bananas we eat, actually most of the time radiation doesn't do much lasting damage. However, some of the time those repairs aren't perfect, either because the damage is just too severe or because the repair mechanism just doesn't quite get it right. And in those circumstances, there's two things that can happen. Either the cell can be damaged, but not so badly damaged that it replicates itself, but it replicates itself now with a mutation, so that the DNA has been changed, but it's copied, and so you get a mutation now carried over into the next cell, and then the next cell and beyond. And maybe over the next 10, 20, 40 years, that mutation gets mutated further because you get sunburnt on holiday, you breathe in some carcinogenic fumes, you smoke, lots of different things build up and cause a sort of cascade of mutations that in the long terms of decades after that initial exposure turns into some kind of health effect. So classically cancer is what we're talking about. Alternatively, the cell might be so badly damaged by the radiation exposure that it is just killed outright and it can't reproduce itself before it dies. Now, in many ways, that's good because it avoids that middle path of leading to mutations and cancer. But if you kill enough cells all in one go, those cells clearly were doing something for you. And so if they all disappear at once, you're going to have some kind of health effect in the short term. So now we're talking hours and days after exposure rather than decades. So just to look at that short-term one in a tiny bit more detail, these are all the things that people classically think of when they think of radiation exposure. So it's your radiation sickness, your radiation burns, say nausea, sort of very nasty things happening to potentially lungs and pneumonitis. And if you have sufficient exposure, it can kill you through multiple organ failure. The key in this case, though, is that we need to get over a certain level of dose, certain amount of exposure, before we start seeing these effects, because you need to kill enough cells all at once for your body to have some kind of health effect. If you just kill 2, 3, even hundreds, your body's got trillions of cells. It doesn't really notice. You need to kill lots of cells all at once. So below a certain amount of radiation, you just don't get any of these health effects. Once you go above that threshold, as you increase the dose, you increase the severity of the effect. So just above the threshold, it may be barely noticeable. It may just feel like you've got a bit of a cold and your immune system's a bit depressed for a while. If as that dose goes up and up, then the severity gets worse until we get to a point where death is unfortunately guaranteed. On the long-term side of things, this is, as I said, sort of classically cancer, but can also be, we now believe, things like cataracts, and also potentially hereditary effects where you're passing mutations on to future generations. Here, the current consensus is there's no threshold. So in theory, you could be exposed to one bit of radiation in your life. That one bit of radiation could cause a mutation to happen in the cell, and in 10 years' time, that mutation causes a fatal cancer. Alternatively, you could be exposed to thousands of radiation exposures every day of your life. You work in somewhere where you get huge amounts of radiation exposure, but none of those exposures go on and cause a mutation, or the mutations that do happen don't go on and cause cancers. So it's a completely random effect, but the more radiation you get, the higher the likelihood that you're going to get some kind of health effect. So here, as we increase dose, we increase the probability that you get some kind of health effect. And that leads to the concept of a LARP, or a LARA. In the UK, we call it a LARP, as low as reasonably practicable. Elsewhere in the world, sometimes it's known as a LARA, as low as reasonably achievable. So that's about pushing down the dose as far as you reasonably can to minimise the probability of the health effects, but recognising that everything we do has some risk. So it's about balancing that risk with the benefits that you get from it. I mentioned dose a couple of times there, just to explain what I mean by dose. So when we're talking about radiation dose, we're talking about trying to quantify the amount of biological harm that is being caused by radiation exposure. So in theory, a given amount of dose, if I tell you've had 2 millisieverts of dose, that tells you that you've had a certain amount of biological harm, and therefore you have a certain cancer risk as a result of that. So dose takes into account the energy that's deposited, but also looks at those different types of radiation. So alpha, as we said, generally clusters its damage, so it's more likely to lead to some kind of mutation. So we give it a higher, weighting factor than something like betas or gammas, which are just got weighting factor 1. And then we also take into account the tissue that's been affected. So some tissues like lung, we need to know to be more radiosensitive than things like your skin. So depending on where that radiation is hitting, we give it different tissue weighting factors. And you combine all of those things together to give you a dose. And the current scientific consensus is that a dose of 1 sievert, which is actually quite a high amount of dose, but one sievert of dose increases your lifetime cancer risk by about 5%. Now, it should be considered that about half of everybody who is living today, or certainly sort of being born today, will get cancer at some point in their lifetime. So you've got a 50% background risk of cancer. What we're talking about is then 5% per sievert on top of that. And as I say, actually a sievert is quite a large amount of dose. The dose limits for radiation workers, for example, in most countries is 20 millisieverts, so 20 thousandths of a sievert. So the whole point is keeping that risk very low. And so just trying to put that into perspective for you. So down here we've got a lifetime cancer risk from a 5 millisievert exposure. So typically that's what maybe the most exposed person at AWE, the most exposed person in a nuclear setting would get in a year, might be about 5 millisieverts. So that means that you have a 1 in 4,000 chance of getting cancer as a result of that exposure. You can see some of the other things on there. Humans generally are not good at understanding and quantifying risks. Things that they know and are familiar with, they generally think are less risky compared to what they actually are. So things like driving on the road, over 50 years of driving, people have a 1 in 85 chance of dying in a road crash. People would probably put that significantly less likely than it actually is, because it's familiar to them. So one of the issues we have to contend with as a radiation protection person is that people generally are much more scared of radiation than they potentially need to be, because they don't really understand it. They can't see it, smell it. They don't experience it as far as they're concerned day to day. So actually the perception of risk when it comes to radiation is in some ways actually more harmful than the radiation itself. But that's one of the challenges we have to overcome. So in terms of actually how we do radiation protection then, we need to think about how you can be exposed to that ionizing radiation. And I want to give you the two main scenarios, which are external exposure and then internal exposure. So external exposure is when the source of radiation, whether that's radioactive material or whether that's an X-ray generating machine, something like that, outside the body. So it's sitting outside the body and it is emitting that radiation, irradiating the body, and as the radiation hits the body and passes through it, it will cause some ionization events. When we're protecting against this type of exposure, what we normally talk about is the ideas of time, distance, and shielding. Basically, if you can minimize the amount of time you're near that source, maximize the distance from it, and also introduce some kind of shielding between the person and the source, all of those things are going to reduce the exposure. And one of the good things about external exposure is essentially once you've removed the person from that environment, the exposure is finished. It's once you've walked away, there's no ongoing exposure. So it's simply for how long you're in the area for. With internal exposure, we're now talking about the radioactive material getting inside you and emitting that radiation once it's inside you. So this is only really possible in what we might call a contamination environment, because there you've got to have the radioactive material in a form where it can get inside you. So it's got to be as a fine particulate, a liquid, or a gas. That's really the only way it's going to get inside you. And so classic examples: decommissioning environments, research labs when using some liquids and gases, or some radiological emergencies. So after a nuclear accident and there's been a release of radioactive material, we may well have liquids or particularly particulates and gases being spread through the environment, which then means that people can get that material inside them. And obviously in this circumstance, that once the material's inside you, even once you've left that contaminated environment, you're still carrying the material with you. So potentially, once it's inside, it's going to be inside you for the rest of your life, continually emitting that radiation. So here, in terms of protection, we need to think about how we stop it getting inside. That's really the main thing. There's a few medical things you can do to try and remove it once it's inside, but none of them are hugely efficient. So the best thing we can do is try and stop it before it gets inside. So we need to consider the routes of entry. So inhalation, which is obviously particularly relevant for this workshop today, but also ingestion, injection through wounds or sort of deliberate injection, or absorption. And for each of those routes, we have to try and think about, is there some kind of engineering system I can put in place? Is there some kind of physical barrier or ventilation systems or something I can use to try and stop the material getting to the person? Can I put in place procedural controls to try and stop the spread of contamination or stop people transferring it? So, don't eat it in a contaminated environment so that you remove that risk of ingestion. And then as a last resort, we can consider personal protective equipment, including respiratory protective equipment, which is obviously the focus of today. Just before I get to talking about RPE specifically, just a couple of common misconceptions I want to outline to you. First of all, people quite often talk very loosely about radiation versus the radioactive material itself. So what you'll commonly see, here's a couple of news reports from the last year or so. So on the left-hand side there, Russia denies its nuclear plant of source of radiation leak. Well, actually, if it was a source of radiation, i.e., that actual radiations of shining out of the plant, imagine it being a big light bulb shining the radiation out, that would be a real issue if you were next to the plant. But actually, once you're a few hundred meters away, that radiation is essentially going to be absorbed by the air, absorbed by the trees and buildings, everything, and isn't going to be an issue anymore. So certainly, if you're not in Russia, it's unlikely to be a problem. What they actually mean here is Russia denies its nuclear plant to a source of radioactive material leak, i.e. radioactive material is being put into the air to then be carried long distances. And if you read the article, it then talks about in Scandinavia, they detected radioactive material in the air and were trying to trace where it comes from. And in a similar way, on the right side there, you can see mushrooms contaminated by Chernobyl radiation. Well, you can't be contaminated by radiation. What that means is contaminated by radioactive material, i.e. the radioactive material released during Chernobyl is now ingrained in those mushrooms, and if you were to eat the mushrooms, then you would ingest some of that radioactive material. So maybe that comes across as quite picky, but I think it's quite important to just have straight in your head the difference between radiation, which is what's actually been emitted by the radioactive material, versus the radioactive material itself. Because for when we're talking about RPE, what we're talking about is trying to prevent the radioactive material getting inside you before it emits that radiation inside you. The RPE is not going to stop radiation. You know, a gamma ray and X-ray is just going to go straight through a respirator in the same way as it goes straight through everything else. In a similar sort of vein, the second misconception I just wanted to put up is the difference between particulate radiation and particulate contamination. So alpha and beta radiations are what we would call particulate radiation. The radiation is a stream of particles, very small subatomic particles, but particles being carried away from the radioactive material through the air or through the vacuum to you. That's different to particulate contamination, where what we're talking about is the radioactive material itself being a fine powder, being a particulate. So if I have plutonium, plutonium is a metal, but if I do a process to it where I machine it or I set fire to it, I can generate fine particulates of those plutonium atoms. Some of that fine particulate may then land on my skin or may be ingested or inhaled by me. And once it's inside, it can then emit alpha particles. But sometimes you hear people talking about people inhaling alpha radiation. Alpha particles travel in a straight line at thousands of miles an hour. You don't inhale alpha radiation, you inhale material that then emits alpha particles or beta particles or gamma rays. And then finally, sometimes people go into an environment, they wave around a Geiger counter or something, they go, oh, I can't detect any radiation here, so it must be free of any hazards. And then they're surprised when we tell them that they really need to wear a respirator. And the problem here is that just because, so an external hazard, you need quite a lot of radioactive material or X-ray generator around to produce enough radiation to be harmful to you in that relatively short period you're present. With an internal hazard, because once it's inside you, it's potentially with you for the rest of your life, you don't need very much of it to actually build into quite a hazard over the next 50 years, 70 years, however long you're going to be alive. So actually, you don't need very much material to give you quite a significant internal hazard. And that means that actually, if all you're trying to detect is the external radiation, you may not detect it despite there being an internal hazard present. So it's about using the right equipment to monitor it and know what kind of situation you're dealing with. So on to my last slide then, which hopefully sets up the two speakers to follow me. So taking into account everything I've told you, where might RPE come into use? Well, essentially, when we're in a scenario where there is a risk that you may be inhaling airborne radioactive material. So what sorts of things am I going to be thinking about? Well, first of all, I've said the non-radiological side, the things that you as RPE experts will be thinking about in any exposure situation. The ergonomics of the respirator, does it allow you to do the job? Does it impact on how your visibility or the ability to enter a space or anything like that? How long are you going to be wearing it for? Can you maintain a seal over that time? And other hazards, that might be present. Actually, radiological hazards may be the least of your worries. There may, if you go into a low oxygen environment, something like that, that's going to dictate your RPE requirements more than the radiological side of things. Thinking about the radiological stuff, though, so first of all, remember the chemical properties of the radiation or the radioactive material, rather. So the radioactive material is still it's a chemical. It is going to behave in the way that as an element or a compound would behave. So different elements, different compounds, despite emitting the same type of radiation, may actually behave very differently in the body. So, for example, iodine, when you get into the body, is taken very quickly up into the thyroid gland, because the thyroid is the only bit of your body that needs iodine. Whereas a different beta emitter, I don't know, nickel 63, may go into the body and may end up somewhere completely different in the body, because although it emits the same type of radiation, chemically it is entirely different, and your body will treat it differently. So considering that the element, the compound you have will influence how it affects the body, where it goes in the body, and actually therefore the amount of dose it can give you. Some materials just go in and come straight back out again. Others are actually absorbed very rapidly by the body and then incorporated into your tissues, your bones, and remain there for a long period. Solubility also plays difference. So even when the element's the same, you can have, for example, uranium, you can have extremely soluble compounds of uranium. That means that if you inhale it, it will very quickly go into the bloodstream. You can have some compounds which are very insoluble, and so will end up lodging in the lung and essentially just stay in the lung, giving a much greater dose to your lung, but not distributing itself around the body in the same way. So considering elements and compounds, solubilities, all that kind of thing plays into it. And I've said at the bottom there, consider the difference between tritium and iodine. So radioactive forms of iodine, like iodine-131, are beta emitters, as is tritium, which is a radioactive form of hydrogen. So they're both gases, they're both beta emitters, but if you inhale a lungful of tritium, most of it you're going to inhale straight back out again, but some of it is going to get incorporated into your body water and be distributed all over the body. The iodine is going to go straight to your thyroid, so it behaves very differently. The physical properties of the radioactive material. So is it a particulate? Is it a gas? Clearly, different filters are going to be required depending on that. And what's the size of the particulate? Again, like any particulate hazard, you need to make sure you've got the right protective equipment for that specific hazard. And then all the physical properties in terms of the radiation types and energies need to be considered. And obviously the concentration of the airborne material, the greater the concentration you've got, the greater the protection factor you're going to need. So the type of RPE you use may well be heavily dictated by the amount of airborne contamination you're expecting to have. And then my final comment is, it may bear in mind that in certain radiation exposure situations, actually wearing RPE to reduce the internal exposure may actually overall be a more harmful thing to do, because if it causes you to take longer to do the job, and the most of your exposure is coming from an external radiation environment, so you've got to run into a room which is heavily contaminated. I don't know how many of you have seen the Chernobyl miniseries, but the guys who were on the roof of the Chernobyl having to throw the lumps of reactor back into the reactor core, for them, actually the main hazard was an enormous dose rate of external radiation. So if in that scenario they could have done the job quicker without wearing a respirator, that may have been overall the right thing to do. So you need to weigh up all these things together. It's not as simple as just, oh, we've got contamination, or we need a respirator. And on that note, that brings me to the end of my bit. So hopefully that gives you a sort of a good introduction, and I will hand over to the other two and then happy to take any questions.
Thank you for that, Chris. Very, very insightful. There are, we've got a trio of questions from Patrick around ionization. So the first one, they're kind of all interrelated. So the first one is ionization more common through A, removal, or B, addition of electrons?
So normally removal, in the sense that what the radiation is doing is imparting energy into the atom, into the electrons, which then gives the electrons enough energy to escape the potential well effect, the bonds which is holding them into the atom. So normally what you're doing is liberating electrons. That said, that electron then has to go somewhere, and so quite often it will go and attach itself to another atom. So you'll actually end up with an ion pair. Sometimes you'll have one negative and then, or one positive where the electron's been lost, and then potentially a negative somewhere else. But the first event is normally a liberation of electrons.
Thank you. And the second duo of questions from Patrick is, what is an example of ionizing radioactive material produced by the addition of an electron or electrons, and then conversely the removal of an electron or electrons?
So I think we're talking about two slightly different things. So the radioactive material itself is unstable because of the nucleus, which I didn't really have time today. If I was doing a whole day course, what I'd start talking about is nuclear physics and what's going on in the center of that atom, and the protons and neutrons and how they interact. So the source of radiation in radioactive material is from those protons and neutrons in the nucleus of the atom. And so there, when you have an imbalance of protons or neutrons, that's when you get radioactive material. So if you consider, hydrogen, so we talked about hydrogen and tritium. So hydrogen, you just have a single proton in the middle, single electron going around the outside. That's not radioactive. If I stick a couple of extra neutrons into the middle, so I've now got a proton and two neutrons, that's now tritium. And that's now radioactive because I've got an imbalance between the protons and neutrons. And so the atom tries to do something to address the balance. And what it does is emit some radiation. So the radioactive material is created by an imbalance of protons and neutrons. Once that radiation, the radioactive decay has happened, and we've got radiation shooting off, it then causes ionization, which is an electron effect around the atom, and that's the chemical bonds then being severed. So, does that sort of answer the question? Yeah. I'm happy to go much more detail of that later on, but I don't want to take everyone's time up going into a whole nuclear physics lecture.
And then a question from Luis. What would be the most cost-effective method to measure, assess possible internal contamination from norm, e.g. urine analysis?
Yeah, so there's various things, and I don't know whether the people about to speak are going to cover this. So you've got a range of techniques to try and assess the internal exposure. So you can either try and measure what's in the air that people are breathing. So you can use room air samplers, you can use personal air samplers where you have a passhead next to the breathing zone, and then measure the radioactive material which is on the filter paper. So that could tell you what people might have inhaled. Alternatively, if you want to try and know for certain what went in, then as you alluded to in the question there, normally the best technique is to try and measure what comes out. So some kind of urine analysis, fecal analysis, and then you work backwards, and there's various excretion curves that say if this much has come out on this day, then this is how much likely went in. You can also do what's called whole body monitoring, where you actually try and detect the radiation coming out of the body. So if you've inhaled some radioactive material, we can actually stick detectors next to your lungs and try and detect the radiation coming out and quantify it that way. That's a more there's less facilities that can do that about the place, but it's technically possible.
Fantastic. Thank you, Chris. Very much appreciated. In the interest of time, we do have the question and answer session at the end, but in the interest of time, I will leave further questions until then. But thank you very much, Chris. Very much appreciated. Just changing back to the slide deck. So hopefully everybody can still see my screen. The one thing I did forget to mention is today's seminar is being held in conjunction with the Society for Radiological Protection. So Chris kindly volunteered on behalf of the Society for Radiological Protection to give this lecture. So again, if anybody's interested in further information about radiological protection in general, the SRP has a very, very good website, and I'm a member. It is a very good organization for those interested in the field. So with that, again, thank you to Chris. We move on to our next speaker, who is, if my will work, is Peter Hillier, who is the Technical Characterization Authority from National Nuclear Labs in the United Kingdom. And Peter is going to give us a case study around nuclear decommissioning, in particular, particulate hazards. Peter has a vast wealth of technical expertise and authority in both site and waste characterization management, spanning more than 3 decades. He's worked in numerous countries around the world, not just the UK, Europe, and as far afield as Japan. So he's got a very, very strong technical background in this discipline. And without further ado, Peter, I'll pass the floor over for your presentation.
Okay, brilliant. Thank you very much, David. Can you hear me okay?
Yep, we can hear you well.
Excellent. And if I can now share my presentation. Okay, is that now visible to everybody?
Yep, that's come through.
Brilliant, thank you. And thanks very much to Chris for an excellent presentation. Stole quite a few of the original parts of my presentation, but actually has set the scene very nicely for what I wanted to talk about. So as David said, more than 3 decades in this sort of discipline, and last 22 years with what was BNFL and moving through into National Nuclear Laboratory, and doing an awful lot of practical site sort of sampling and characterization work. And as I appear today on the screen, I often appear not on the screen, looking more like that. So very used to the hands-on practical aspects of deploying respiratory protection, but also all forms of rad protection, and keeping myself and my colleagues safe undertaking this sort of work. Because I wanted to, as I'll cover in the later slides of this presentation, we do face some very, very hazardous conditions. There are some quite unpleasant materials we have to be involved with, hands-on with, sample, and we obviously have to keep our staff safe, protect ourselves, and make sure we can deliver the particular decommissioning challenges that the industry requires us to address. So in terms of my presentation, oh, sorry, I seem to have jumped a slide there. Oh. I don't seem to be able to go back. Bear with me a moment. Oh, that's right. Okay, sorry, I thought I had a content slide in my presentation, but it seems to have disappeared. But what I actually wanted, what I'll be running through is an introduction to the inhalation hazard, which, as I mentioned, Chris has very well covered in his presentation, and also the principles of the LARP. But then want to look in a little more detail at the hierarchy of hazard control, and then how we actually implement that in terms of radioactive contamination control, both in terms of dose and contamination in a decommissioning environment particularly. And I'll be concentrating, when we get to that section, very much on a individual boundary between categories of C2 and C3, which I'll explain further shortly. And it's at this point in the contamination control hierarchy for contamination that we really start to deploy respiratory protection in earnest. And then I'll move into a case study just showing how, on a project I was working on, we actually put significant engineering and sort of practical protocols in place to prevent the requirement to need respiratory protection. So I'm trying to engineer out the problem rather than having to rely on sort of RPE, respiratory protection, etc. And then just look at some of the types of respirators and respiratory protection we use in the UK in our nuclear industry, and then look at how we can potentially remove the hazard completely to avoid ever having to use respiratory control. So the slide I have up on the screen at the moment, as I say, Chris has covered excellently, but really what we're talking about is the internal exposure. So Chris mentioned dose, external dose, and there's a difference between external dose, external contamination. But what we're very much concerned with is the actual radiation getting into the body in terms of respiratory protection. And the main route is by inhalation or ingestion. So you can get it through the skin, cuts, grazes, etc., injections, but the predominant risk is inhalation, and that's particularly true when we're looking at a decommissioning in a very dirty environment. So if we look at the different types of radiation, again, I won't labor this too much, but I'm particularly keen to just point out again the sort of extreme radiation damage that can be caused by alpha particles once inside the body. As mentioned by a previous speaker, if it's on the skin, if it's outside the body, it can't penetrate the skin, so it's likely to cause very little harm. But once inside the body, it's a different situation. And I'm sure we're all familiar with Alexander Litvinenko case, very sadly poisoned using polonium-210. That's an alpha emitter. It was the alpha emitter that did the damage. And actually, it's been calculated that you only need 0.089 micrograms of polonium-210 to kill somebody. So as you can see, it's a very, very small amount of material that can have a very, very devastating effect on a human body. So controlling the environment, preventing even the smallest amounts of particulate material getting into the body is essential when we're looking to keep our staff safe. So again, the principle of ISRP was discussed extensively by the previous speaker, so I won't spend too long dwelling on this particular slide, but simply to say it's clearly our overriding principle, keeping the dose down. But interestingly, the mention of ALARA and ISRP. ISRP is the UK definition that is enshrined in law because it links the Health and Safety at Work Act. And also, the key principle for ISRP for myself is very much in terms of radiation protection. We're looking to work down. So we're trying to drive down the dose to operatives, not work up to a limit. Now, I believe there are certain countries in the world that do actually allow you to work up to a limit in terms of assessing radiation risk. Happy to be challenged on that, that's just my recollection. But we look to try and work down away from that limit and try and drive the dose down and keep the dose as low as we possibly can for operatives. And that, as Chris mentioned, leads very well into the ISRP discussion. So how do we do that? Well, one of the main tools we use is the hierarchy of hazard control. Now, obviously, at the top of the tree there is to remove the hazard completely. If we could remove that hazard, so as mentioned previously, moving away from a radiation source, you've removed the hazard, preventing anybody coming in contact with contamination, you're removing the hazard. But then we move down through engineering controls, so shielding, containment, ventilation, and keep moving down through the classification and then say systems of work, with personal protective equipment very much being the last resort. So I personally don't want to be working in an environment where I'm relying on my respirator to keep me safe in that working environment. That is very much a last resort. And I hope to never have to actually need it, even when I'm using it. So we always work to try and particularly remove the hazard where we can, or stay at the top end of that pyramid around the engineer controls and classification of areas. Those two are our primary areas we want to work in. And particularly when we start looking at classification of areas, which we'll come on to next, it's very much around this C2, C3 boundary that I've mentioned previously. So this is taken from some guidance at Sellafield, but is generally sort of broadly accepted principle across the civil nuclear sites in the UK that I've worked on. And it very much designates areas as radiation classification areas and contamination classification areas. And as you can see on the screen now, there's the various classifications of R0 to R5, and that is all just about the dose you receive in that area. And obviously the dose you receive in that area, it's measured in units per hour, in microsieverts per hour. And if you're trying to control dose in those areas, it's quite simple. Spend as little time as possible in there and use your shielding, etc. The contamination classification is the one I really wanted to look at in a little bit more detail, because as you can see, highlighted on the right is the airborne contamination level for controlled area C3. So this is about contamination and loose contamination that can become airborne. And once you get into your controlled areas up into C2, C3, when you get to C3, that's when the airborne contamination levels really become an issue. And you have to have in place respiratory control and engineered controls and barriers and protections to actually enable you to work safely in that area. So it's a very clear dividing line. So we, whenever possible, aim to deliver our work in a C2 environment, particularly when we're doing sort of sampling and decommissioning activities, etc. And I'll come on to reasons for that shortly. But certainly, as you can see from the levels of contamination, as soon as we get any significant airborne contamination, we move into a whole different set of controls and regimes for managing that work. So to illustrate this boundary, so we have an example here. So the small picture you can see on the left, that is myself and a colleague working in a C2 area. As you can see, we're wearing coveralls, sort of basic protective equipment you would expect to see in a C2 area. So coveralls, face visors, because we're actually working with liquids and there is a splash risk, and gloves. And you know, we can operate quite freely. Communication's quite easy. It's a relatively pleasant working environment. So then we start, if we then have to upgrade this to C3, we start to have to define that area and put controls in place. So within our C3, within our C2 area, we have to define a barrier, and that barrier, one side is C2. Once we get over that barrier, all the C3 controls come into place. So we have a barrier to enter our area. We then, within the area, we have to start talking about measuring the actual airborne contamination within the C2 area. So as we're measuring airborne contamination within the C2 area, we have to have some way of measuring it in real time. So we need to know in our C3 area if there is airborne contamination levels are increasing above safe levels. So we have to have some method in place for measuring that in real time. And we have to be able to extract air from the C3 area to maintain a flow of air over the barrier to prevent contamination moving from C3 to C2. But we have to draw that air out and filter it before it's released to keep the C3 area or the contamination within the C3 area. So we have an extraction unit that takes the air out of our area. By putting the extraction unit in, we have an airflow across the barrier, as I mentioned, to keep pulling air from the C2 to the C3 area. So we're always going from the cleaner area to the more contaminated area in terms of our airflow. And then we have our C3 area. And when we get into a C3 area, for example, as you can see, the levels of RPE is much higher. We have respirators on, we have hoods. In fact, when we're in C3, it's a full change of clothing, right down to basic underwear, coveralls, 2, sometimes 3 pairs of gloves, depending upon the activity, full respirators, sealed to the outer garments as well, normally taped, so you don't get any air entering or in contact with the skin. And that brings its own challenges in working in that environment, which we'll look at shortly. So just a couple of examples I just wanted to share to show a couple of C3 tented examples of areas we've worked in. So this is within a plant, existing C2 area, so people can walk to in a normal RPE, coveralls, etc. You can enter that area, you can work in that area. But we were opening tanks and we were removing material, contaminated material from the tank, so we had to lift the categorization of that area to C3. So we constructed temporary tenting out of polythene. And as mentioned previously, you can see in the foreground of the left picture, the C2, C3 barrier is a box where the health physics support will operate and monitor you in and out of that C3 area. And then you go through an airlock into that C3 area, which is sort of doorway set in the back there, to allow you into the area to undertake the work. So it's quite an onerous undertaking, setting up the initial C3 area in the first place. And you can see on the top of that image again on the left, you can see the ducting for the ventilation system, etc., all of which has to be installed before you can operate. So as an example of how we manage this sort of hazard when we're looking at a particular piece of work, this is a case study I put together off a sampling program we undertook on a Magnox site within the UK, and we were looking to sample sludges and waste materials within tanks, so it can be characterized and categorized for disposal or treatment and disposal. So there's a number of tanks, but this one particular tank was flagged as having a potentially high alpha content within the waste. As mentioned previously, clearly alpha gives us a really significant issue when it comes to airborne contamination. And there was concern that by removing material from the tank, we may contaminate the C2 area, and we may be looking at lifting the levels to C3 to allow us to safely operate and sample in that area. So this was a challenge. How do we do this? Do we just straight C3, respiratory protection, etc., and all the challenges that presents, or is there some other way of doing it? So we developed a fairly simple and straightforward solution. We took what is, as it looks at, a galvanized steel bucket, and we connected to the bottom of that steel tube that entered the tank. So all our sampling was done through that simple funnel arrangement. And to mitigate the risk of airborne contamination, as the sampler was removed from the tank each time, it was washed down using just a simple low pressure water spray to wash all external contamination off that sampler into the tank. And that acted not just to wash the contamination off, but keeping everything wet minimizes the risk of an airborne contamination, because we're not allowing things to dry out. We're not allowing particulates to become airborne. We're keeping everything that's potentially contaminated wet or it's contained. So once the sample is withdrawn, how do we manage it then? We've pulled the sample out of the tank. It's potentially clean, but we're not 100% sure it's totally clean on the outside of contamination. So we actually draw it up, the sample up into a plastic bag. Very simple, large plastic bag, cable tie the sampler top and bottom so it's contained fully within the bag. And then, as you can see in step 4, that sampler still in its bag is exported from the work area to a glove box that was set up next to the tank, and the sampler still in its bag is imported into the glove box through the airlock, and then the operative in the glove box can take the sample out of the bag, take the sample out, package the sample into a sample container, clean the sampler, and it can exit the airlock for the next sample. Now, quite a time-consuming operation, and did add significant time in terms of actually the program of work, but it meant that the risk of airborne contamination had been fully mitigated without the need for all the expensive up-revving to C3. We didn't need all that additional tenting and equipment and manpower required to actually deliver that. And actually, there's also a saving in terms of long-term disposal of waste and things, because once we built that tented structure, that would then have to be disposed of, dismantled and disposed of afterwards as a waste stream as well. So there's all sorts of arguments as to why this was a much better way forward, as well as just simply control the radiation dose. But it controlled dose and allowed us to complete that work safely at the C2 level. So Why do we want to spend so much time in C2 rather than C3? Well, as I mentioned previously, C3 is not very pleasant. Once you need to set up that additional tented structure, you need the containment, you need all the equipment, etc. You need more people. You need a permanent barrier monitor on the C2, C3 barrier to help you dress and undress, to monitor you in and out the air, etc. And as mentioned previously, the amount of additional equipment required, air samplers, EnviroVac units, etc., is quite considerable. The RPE, you need a lot more RPE, and you also produce a lot more secondary waste. So every time you enter that facility and come out, the secondary waste produced, there's coveralls, etc., need to be disposed of, respirators that need to be cleaned and refitted, etc. So there's a lot of work, a lot of equipment required. You also find that when you're in the C3 areas, it tends to be shorter working times at the workplace. In a given shift, it takes a significant amount of time to actually get an individual from outside the area through the various change procedures and up to the workplace to physically work. And once you're there, wearing all that equipment, taped into effectively PVC suits, it's very common to become very hot very quickly, and heat stress and exhaustion is a real risk that needs to be managed. And it's a difficult one to manage because it's on an individual basis. People deal with heat differently. And some people can work for hours in those conditions. Some people, after a few minutes, are overwhelmed by it. So there are real challenges in terms of the heat risk, heat exhaustion and risk in those areas. And a topic we've discussed quite a lot is communications. As you saw from the previous image, we're wearing full face respirators. We're taped into our RPE, our suits. We have vent units operating near us. They're often inside plant and noisy areas, and communicating with your colleagues can become a real challenge. So actually just straightforward communications, you have to do a lot of active listening and repeating instructions to each other to make sure you both understand what you're actually required to do and what you're actually doing. So it is very challenging to complete this work safely. And of course, we all have to consider cost. There isn't a magic money tree. We need to try and do things as cheaply and as efficiently as possible while maintaining safety. So C3 gives us some real challenges in terms of work. So as we're talking about respiratory protection, clearly once we're into C3, we obviously have to ensure we have the correct respiratory protection in place. And these are just examples of types of some of the respiratory protection that are used in the nuclear industry, and most of which I've had experience of, not the full suits, thankfully. I don't fancy that, but certainly the images on the left, standard C3 respirators, myself and colleagues doing work on various sites, sampling ponds and tanks, etc. And the image in the bottom, second left, that's actually in a confined space, as well as being on having a radiation hazard to deal with. We're actually sampling a tank that was also in a confined space as well. So a real challenge, and trying to operate in these areas with respirators sticking out the front of your face and the side of your face, etc., can add an extra level of challenge to completing the work. So the image in the middle in orange, and apologies for the poor image there, it's the only one I could find, but that was actually the working environment within the orange tented areas I showed previously. And again, they're tornado hoods. So rather than having a respirator on your face, the respirator is on a belt around your middle, and you're blowing fresh air through a hood across your face. So it always maintains a positive pressure. So you can't get air coming into the hood. It's always expelled outwards. And in all honesty, from a practical perspective, these are much better to work in than respirators. They're much more comfortable. They are much more cooling. But again, they are quite noisy. So there's additional challenge of communication using those respirators. And then on the right-hand side, we have the full air-fed suits, which, as I mentioned, I've not actually operated in those, but colleagues that have said actually they are more comfortable to wear than the respirators and the tornado hoods, because you are completely enclosed, but you're having fresh air pumped in all the time. So in some respects, those suits are actually better at preventing things like heat stroke, etc., or heat exhaustion. But again, they're very expensive to maintain and operate, and they're very easy to tear and damage when you're operating in them as well. So there are pros and cons for all these different types of respiratory protection in our industry, in our environment. So ultimately, and this is my final slide, so I hope that has been of interest. Apologies, a little bit short. But ultimately, what we want to try and do, particularly in the nuclear industry, is remove the hazard completely. Can we actually remove the respiratory hazard and not, put people into those environments? So an awful lot of work, top of the hazard hierarchy, is to remove the hazard altogether by deploying robots and sort of remote operations. So our industry has a very strong driver in the area to develop robotic approaches, artificial intelligence, etc., to deal with the decontamination and decommissioning challenges that we face in the future. I personally believe there'll always be a place for people. There are some tasks that certainly currently technology people are better at doing, and also there is a cost to that element as well. Developing robotic components is very expensive, so there will always be that challenge to taking the people out and putting fully automated systems in. But it's certainly a large area of development in the nuclear industry, and it's one that will only grow as the decommissioning challenges and the dismantling of the first generation reactors in the UK sort of builds up ahead of steam, and we start dismantling the reactor cores and the more challenging parts of the facilities that we're left with. And I think that's all I had. So David, hope that's okay, and back to yourself.
Fantastic, Peter. So thank you very much. There has been a raft of questions come in. So I'm going to ask a few from the Q&A. So the first one is from Michael. He said, using the ALARP principle, why is RPE not always required, irrespective of the airborne contamination level, e.g. C1, 2, and 3?
That's a good question. I would probably have to talk in detail to our radiological protection advisors, of which I'm not. But I would imagine there has to be there is a limit at which the sort of risk posed by that airborne contamination is considered acceptable. In those sort of areas where you're talking about almost unmeasurable low levels of contamination, if there's anything there at all. And also in the if you looked at the C1 and C2 areas, there's a difference between fixed contamination and loose contamination. Now, I'd have to look at the detail and look at the actual guidance in more detail, but if the contamination is fixed, it's still classed as contamination, but it can't become airborne. So you've much less risk of actually inhaling that material. If there is a significant amount of loose contamination, then clearly the inhalation risk becomes higher. And some of it, I do believe, is practical constraints. Otherwise we'd all be walking around full time in respirators, and the level of hazard doesn't necessitate that kind of level of PPE.
And a follow-on question from an anonymous viewer: how have the levels for each classification area been chosen, e.g., DAC, etc.?
Yeah, I'm sorry, I really wouldn't be able to comment on that. They've been developed by those that I presented have been developed by Sellafield themselves, and we presented those in a safe system of work, and they've been approved by our RPA. So we just work to those levels. Fantastic, thank you.
And this is a really interesting question from Ian, who now works in radiological protection, but he started out in microbiology, and he's worked at the very highest levels in the country. From a microbiology virology perspective, where they separate the person from the hazard by using glove boxes and isolation beds as far as practicable. And he said this approach seems to be less well developed in the nuclear industry. Do you have any thoughts on that?
It's an interesting perspective. Within the nuclear industry, we extensively use glove boxes, fume hoods, etc. It's the example I provided was, sorry, there's a bit of an echo there. The example I provided was quite a specific challenge that we use glove boxes to actually mitigate a specific hazard. But in terms of decommissioning, I'm not sure, because
Could I possibly come in a second on that one, David?
Yes, sure, Chris.
Sure.
Yeah, sorry, I don't want to take. I think it's a really good question. I think my experience is that we do use glove boxes and all of the tools you described in the sort of biology sector very extensively in operational buildings, so buildings which are designed and still in operation in their intended use. I think what you see quite a lot of in the nuclear industry is buildings that are now undergoing decommissioning, which is exactly what Peter was obviously showing there. And because of the age of the nuclear industry, some of our oldest buildings at Sellafield and Aldermaston and Dounreay and all over the place are now in decommissioning. And that's where you do end up with having to use all of the things that Peter was just talking about, because you've deliberately cut up your glove boxes in order to decommission them. I guess on that front, a difference with something like virology would be that, and I'm clearly not a virology expert, but my understanding would be that I guess if you, after a while, you could end up with you could clean it down so that you essentially are free of contamination before you do that decommissioning. Whereas clearly, if you've got sort of, radioactive materials with half-lives of millions of years, that's not really an option. So you've got to deal with that contamination as you decommission it.
Yeah, I'd agree with that.
There are quite a few other questions, Peter, but in the interest of time and to give Paul his presentation, I'll come back for the audience's benefit. I will come back to the questions that are in the chat box in the Ask the Expert session afterwards, but to give Peter a bit of a breather. But thank you for that, Peter. Very, very insightful presentation. And then, so as we move on, I'm going to share my screen again, so hopefully everybody can see my screen. This is a slight alteration to what advertised, but nonetheless will be just as thought-provoking. So it's my great pleasure to introduce Paul Cooper, who is the group leader for nuclear threat reduction operations at the Atomic Weapons Establishment in the UK. And Paul is going to give a slightly different perspective view, but this time it's going to talk specifically about cleanup operations around the Polonium 210 release that happened during the Alexander Litvinenko assassination in London a few years ago now. So just if my PC will wake up. So as I mentioned, Paul works for Atomic Weapons Establishment, is a vast experience in emergency response management across the AWE estate. He also holds a master's degree in emergency planning management, and he's been involved in many multi-agency exercises and real-life events in the United Kingdom and across the world over a number of years. So it is my great pleasure to pass the floor over to Paul. So over to you, sir.
Thank you very much, David. Can you hear me okay?
Yep.
Perfect. Okay. Just bear with me one moment and hopefully my screen will magically appear. There we go. Sorry about this, slight gremlin. Okay. Are we working yet? No.
Not yet. It's thinking about it.
Apologies, bear with me. Let's try again. There we go.
Yep, it's coming through. Yep, there we are,
Paul. Perfect. Good. Apologies, everyone. A good day to you all. Thank you very much to David for the opportunity to speak to you today, and I hope everyone's staying safe and well. So yeah, my name's Paul Cooper. I work at AWE in the UK, the Atomic Weapons Establishment. I have done for far too long now, as long as I care to remember. And I'm going to talk to you today, not for very long actually, but on a few specific matters, really relating to how things change a little bit when we consider the use of respiratory protective equipment, or RPE, in an emergency or a crisis environment. So I'm going to talk a little bit about why it is different, some of the things and some of my experiences as to what we need to consider differently to perhaps if we were working in a normal operational environment within a nuclear facility or a radiological processing area, or a decommissioning environment, as Peter's alluded to earlier. And I guess not only why it's different, but what that means. So why does that matter, and why does it cause us some problems, and how do we have to think a little bit differently about it? And also some practical considerations about what can be done to mitigate some of those issues and challenges. I'll then go on and just briefly talk about a bit of a case study. As David mentioned, the poisoning of Alexander Litvinenko in 2006 in London was the most recent and probably the only known major radiological event, certainly in the UK and probably in Europe. There have been some other very significant ones globally, but this is certainly one that's lived long in the memory of many of the folks at AWE who were involved in the response, and also our radiation protection community that provided advice not only to our own people to keep them safe, but also to some of the authorities involved in the response to the incident. In particular, the Metropolitan Police, who police the London area, obviously, who need to keep their own people safe in doing their investigations. And then we'll draw a few conclusions at the end of the session, and obviously happy to take any questions in the feedback session a little bit later on. Okay. So I guess in terms of why it's different, well, we're looking at a number of challenges that we would just simply not see in the normal workplace when we're dealing with exposures and releases of hazardous materials. Radiation is just one of those, or radioactivity is just one of those, into an uncontrolled environment, into the public domain. So the things that we would never expect to see in our workplace, for example, pigeons and ducks and people wandering past, members of the public, all of those things we just do not see, because we exclude them from our working environment because we can, and because it's the right thing to do to protect them and to make sure that our operations are properly controlled. So the environment is a massive consideration when anything goes wrong, and we have to start responding to things that are outside of those controlled premises. There are all kinds of considerations that come into play, not least things like access. Peter, in his presentation, alluded to the fact that between certain levels of contamination area, you could set up physical barriers and so on. Well, that may just not be possible in a radiation incident when you're responding to something. Equally, achieving airflows that protect people from potential particulates in the air, it may not be possible to achieve certainly in the way that you would do in a controlled environment. Obviously, the weather plays its part, and I think in London in 2006, the weather was pretty much as it is at the moment, certainly in the UK. So dreary, a little bit windy at times, raining a bit of the time. But if you look back to the Salisbury poisonings, which weren't radiological, but still required a large response, and a lot of people having to use RPE and so on, they were dealing with snow on the ground, they were dealing with freezing conditions, and the subsequent issues that came around when some further contamination was found just down the road from Salisbury. That was found in the kind of spring of the following year. So they were then working in 30+ degrees temperature. So they had real challenges with the extremes of temperature, and exposure to the cold, but also the heat stress that Peter alluded to in his presentation. And of course, the eyes of the public are usually focused very sharply on these incidents when they happen. So there will be representatives from the media that want to know what's going on, and want to understand, sometimes before the politicians and the authorities even understand, what's happened, who's at fault, and what's being done about it. So there will be people trying to intrude, and some of those people will take sometimes some fairly large risks, either knowingly or unknowingly, to try and get the best story and the best media coverage that they possibly can. Of course, the environment that we're working in may not just be a radiological environment. So it may be that there are other types of hazard, and they may just be conventional hazards. So, for example, stepping outside a sushi bar in central London, you're basically in the middle of one of the largest traffic thoroughfares in the capital, and you're transporting quite a lot of heavy equipment and various other items and forensic samples, etc., across a busy road. Now, that's not a radiological risk, but it's probably more likely to do you any harm than the radiological hazard will do if you're protected properly against it. And of course, as mentioned earlier, the difference between the radiation hazards. So if you've got a situation where you have particulate contamination, so particulate radioactive material, as was the case with polonium, which is a risk to get into the body, then you can protect yourself against that fairly effectively with respiratory protection. If there's also that external radiation hazard that Chris talked about in depth earlier, you may find that you can't, there isn't one effective way of protecting yourself against all of those hazards. So you then get into some very complex thinking about, do you use a combination of radiological respiratory protection as well as external shielding and limiting the amount of time you spend in an environment and all of those things. And of course, when you first arrive at the scene of one of these problems, you don't know how much is there. You don't know there's anything there potentially, but certainly if there are indications there might be something there, you're going to have to do a lot of work to characterize the levels of contamination and material that you're going to find at that scene. Of course, in all of these events, there is a sense of massive urgency. So you don't have the same time and luxury of, room headspace to be able to plan and really work out in detail what you're going to do and take that through all of the relevant committees and approvals that you would normally do for a piece of hazardous work such as this. You are working very much in a crisis, so decisions are expected to be made, and they are made very, very quickly. And there were also a number of conflicting priorities. So if you look at the Litvinenko case, obviously the major priority for the police force who were responding at the time was to keep the public safe, absolutely, but also to investigate the incident, what had happened. They treated it as a crime, so they needed to gather evidence and make sure that they had enough, should there ever be a subsequent, prosecution or court action or whatever it was, to make sure that would be effective. So there were lots of conflicting priorities, and even among the police officers that we worked with, some were focused very much on public protection, some were focused very much on the investigation, and others were focused very much on just managing the overall consequences of the event. So there were lots and lots of conversations, and one single risk assessment has to be really, really comprehensive and really effective in order to cater for all of those priorities and ensure that they're managed safely and that no one comes to any harm as a result of the response actions that you're taking. And one thing as well that came out of that incident and others and exercises that I've been involved in, but particularly the real incidents when they occur, is there is a phenomenon, it's colloquially known as disaster addiction. So people will tend to work longer, harder, and for greater durations of time than probably they should, and certainly that they normally would, which is fine on one level. It's really, really good that people want to commit and they want to do the right thing and they want to help to resolve these major national issues, as they arise. However, we mustn't lose sight of the fact that the equipment that we give them and the tools and the protections that we ask them to use may not be designed to go that extra mile in the same way that those individuals are. So it's really important that we don't ask people to do too much, and that we don't plan. We do plan for their natural tendency to work for a bit longer and a bit harder just to get the job done. and really guard against that and make sure that doesn't happen to the detriment of their health and well-being. So what does that mean? Well, I've mentioned, risk assessments. It all starts with the risk assessment, the ALERT principle, the hierarchy of controls. Unfortunately, when incidents occur, we start off usually fairly close to the bottom of that hierarchy because we don't have enough information and we're not in the right environment to be able to manage those controls, certainly to eliminate hazards, because we don't know sometimes what the hazard is and how much of it there might be. But also things like engineered controls, with airflows and with barriers and classification and designation of zones and so on, simply may not be possible, particularly if you're working in the public domain, in an uncontrolled environment like that. I've also found that actually many of the specialists that are required to respond to these incidents, because, for example, people that have lots of experience in forensic evidence collection, they don't normally wear respiratory protective equipment. Okay, they are used to actually, rather than being protected themselves, they're more used to wearing equipment or clothing that protects the forensics and protects the evidence that they're there to collect. So it's really dangerous to assume that people will be highly experienced in wearing, protective equipment, particularly in this kind of environment, in the way that certainly, Peter and his colleagues clearly are. And of course, things change. So, as an example, in 2006, we were called to one scene, which quickly became, I think, probably 3 or 4 scenes by the second day. Within a week, that had become 40 plus scenes that the police were interested in investigating, each one of them different. So the risk assessment that we were that was being prepared from a radiation safety point of view was continually being reviewed and updated, and I mean literally continually on an hourly basis as a new problem was identified or a new location. And that is, firstly, that's really exhausting for the people that are constantly trying to, analyze and assess all of these unknowns and turn them into some practical protective measures. But also it's quite risky in terms of making a mistake, because it's really easy to just to overlook something, and particularly when there's lots of information coming in, not all of it has been corroborated. So sometimes you're working on hearsay and you're working on unconfirmed reports of things, and trying to, as best you can, shape your risk approach, your hazard and your risk assessment approach around that. And equally, because of all those unknowns and that uncertainty, assessing what we might term the collective risk. So, the risk overall to a particular team that might, in a normal operation, might be able to effectively share the risk of the dose that they might get, the radiation dose they might get. That becomes immensely complicated in this kind of operation. So, a real challenge. And of course, from an RPE, a respiratory protection point of view, getting the right protection to match that level type of hazard in the environment that you're in is really, really difficult. There are very few, as a whole, competent emergency responders that will turn up with exactly the right RPE for the task that they're going to do, in a certain contaminated environment, because we don't know what that environment is going to look like until we turn up. And equally, then that might mean that we need to do things like just-in-time training, so training almost on the spot for people. And that was certainly the case for Litvinenko. We did some training and awareness pretty much on the day for some of the officers that were involved in that work, to make sure that they were really comfortable and properly competent to use the protective equipment in the right way, but also just to understand the overall context and the hazards that they were dealing with. And for them, I think that was invaluable, having people not so much like me, but certainly like our radiation protection team, available to provide that insight and guidance. So we weren't making it up as we went along, by no means, but things were very dynamic, and things were changing on almost an hourly basis. And of course, if you're going to start using complex respiratory protective equipment, and by that I mean, you know, things that require positive pressure air feeds or self-contained breathing apparatus, usually there's an infrastructure that will support that. You know, so there will be air tanks and compressors in facilities where we know we're going to be doing these kind of operations. And in fact, at AWE, we have that kind of infrastructure installed when we know we're going to decommission a building. So we've got that capability on tap. But obviously, in an incident like that, or any kind of radiological incident, that infrastructure will not exist. So it either has to be brought in, or we have to find other ways of minimizing the need to use those really complicated respiratory protection solutions. And of course, we need to be cognizant of mixed hazards. So although, you know, the Litvinenko case turned out to be polonium, there were a number of other scenarios and other theories that were at play. So conventional poisoning and various other you know, potential causes of his illness, sadly, that were being explored. So it would have been wrong to assume that it was definitely a radiological problem. It may well have been a number of other things, some of which may have required a different approach to protective equipment and you know, and risk assessment. So what can be done? How can you plan and prepare for these unforeseen dynamic incidents? Well, risk assessments just have to be flexible. In particular, things like hold points for the levels of radioactivity that you might be able to measure need to be very dynamic and flexible, but also probably somewhat conservative in the first instance, so that particularly those people that are responding initially are not put at any unnecessary risk. So the idea of that is you might enter an area, and we might be talking just the domestic residents, right? It's you know, someone's house, someone's home. You walk in, you need a strategy then for understanding very quickly what that hazard is and how significant it is. And if you reach a certain level of hazard, a certain detector reading or a certain concentration in the air or whatever it might be, you need very quickly and very effectively to be able to stop, withdraw, and reconsider your risks. So that happens and happened a great deal during the Litvinenko case, and happens a lot on the exercises that we do as well. And it really is all about that onion layer approach. So it's a similar principle to, in particular, that Peter talked about with the C1, C2, C3, so on. Those areas, increasing hazard as we get, if you will, further into the problem. And that will require actually a broadly kind of similar approach to our selection of respiratory protective equipment. The other thing we did a lot in 2006 was identifying and using natural barriers. You know, so it can be something as simple as the front door to a property, but you know, it may well be that we were using you know, hotel corridors or sections of hotel corridors as kind of secondary areas before we actually got into, for example, a hotel room of interest, and so on and so forth. So it really is just finding those natural barriers within, you know, the environment that we're working in, wherever they exist, because it's much simpler to create those barriers quickly if they're already there, and create those demarcations, than it is to try and build or construct them quickly if they're not there at all. And one of the other things that's really key is where you've got multi-agency responders working together, is an early conversation between those agencies about a collective approach to the risk assessment and to their protective equipment strategies and policies. If they can be aligned really early on and people can agree where they're going to share an approach and where they have to differ because they might be doing different tasks, for example, with different risks associated, that's probably the best recipe for success. What you don't want is someone stood there, if you look on the left of the slide, someone in an oronasal mask, you know, in a PPF2 mask, you know, stood next to someone in the breathing air kit that's on the self-contained breathing apparatus that's on the middle of the slide there. standing next to each other and looking at each other wonderingly as to why one's wearing one and the other's wearing the other, if you can possibly avoid that. And trust me, it does happen. Thankfully, more on exercise than in reality. I only put this slide up really just to I guess reinforce that point about the dynamic nature of the hazard and how we should use the principles that we learn in our day role in our normal in our normal operations. Peter's case study, a fantastic example of that. And we should be applying them. We shouldn't be trying to do anything that's completely new and completely novel. But what we should be doing is applying what we know in a novel situation. So, the operational burden of using a PP2 mask, and again, these the numbers here are arbitrary, so don't quote me on them. But you can wear one of those for around about 4 hours. They're disposable, single use, relatively very cheap, very widely available, probably given the pandemic, even more so. And you can train someone to use them in probably minutes. You can give them some advice on how to fit them and how to make sure that they're properly worn, and away they go. Right the way through to self-contained breathing apparatus at the bottom there, which gives you a great protection factor, but you can sometimes only wear it for a few tens of minutes. So there's a massive operational burden that comes with that, and you need to be mindful of that and really optimize those tasks that you need to do in that kind of very high level protection, to make sure that you're not overusing that solution unnecessarily. And there's a real art to that. So the response to these kind of incidents, usually you'll see, and there's lots of things. If you go online, there's lots of kind of, if you Google like incident response zones or CBRN zones or any of that kind of stuff, generally speaking, you'll find that things are divided up into a few different zones, like that onion layer that I was talking about, which is fine in concept. That's great, and you can have some barriers, and you can have some controls, and you can have some specifications for the protective equipment that you would wear within each of those zones. Actually, what we found on the Litvinenko case was there were some items that were within what you call the hot zone that were extra hot. Okay, so there were some specific artifacts and items that were really, really very heavily contaminated, and I'll talk more about that in a moment. So you may need to really think about working in the hot zone and the general levels of protection you need in the hot zone may be acceptable, but you might need in certain parts of that hot zone to isolate some specific areas. Hotspots might be a name for them, where you need even higher levels of protection, and you really focus that operational burden of that additional equipment and support and training and so on. You really focus it on those areas where it's really needed. And again, it's complicated, but that's the approach certainly that was taken for Litvinenko. So on to the case study, and it's a couple more minutes and then I'm done. But yeah, just wanted to, I guess, draw together some of what I've said into that experience of London in 2006. There were multiple scenes, 40 plus scenes, pretty much every single one with a different hazard profile. So there was a different distribution of radioactivity and hazard across those scenes, each and every one of them. Ranged from hotels through to vehicles, cars, domestic properties, sushi bars, you name it. So each and every one had a different hazard profile and required effectively a different interpretation of the risk assessment to make sure that it was fit for purpose in that environment. As I've mentioned, a number of the agencies, but in particular the police forensics teams, were very used to protecting the evidence. So protecting what it was that they were trying to recover, the contaminated material, ironically, rather than protecting themselves from any hazard that might cause them harm, either in the short or the longer term. Some of those contamination hotspots that I mentioned in the last slide were really quite discrete items. So there were some specific items of clothing. I won't go into the detail of where and who and how, but there were some specific items of clothing that were very, very heavily contaminated. And we could operate in the zone, in the area, which happened to be a domestic residence. We could operate in that hot zone as long as, and everyone who went in there was aware that there was some clothing in a certain part of that environment that was effectively a hotspot, and that anyone who was going to go and disturb that needed to up the level of protection that they would use in order to deal with those items. So that became the way that we got around those problems. We didn't designate the whole area as a very high area because it would have stopped a lot of the other work that needed to urgently take place in order to pursue the investigation. The monitoring results that were taken, so the characterization information about how badly contaminated location A, B, or C might have been, was shared across multiple agencies, as you would expect. So AWE did a lot of monitoring work and shared that information. Other agencies as well, Public Health England, who have recently been renamed to the Health Security Agency for the UK, and I think back then were called the Health Protection Agency, if I remember correctly. It was all one organisation. They also had specialists out monitoring, and there were one or two other agencies as well that provided some support, both to the initial response phase, but more so actually for the cleanup of that material. But as I mentioned, all of those organisations had slightly differing policies on radiation dose and protection, and they also had access to different pieces of protective equipment. So they would use something slightly different to another agency. And there was a risk that could cause confusion, because sometimes when you dig into the detail of some of these policies and you dig into the specifications of some of the equipment, it's not quite comparable. Where you think it might be ostensibly on the face of it, it's actually slightly different. So there's quite a bit of discussion about just making sure that we were all up to a minimum standard of protection when we were operating in a particular environment, so that so everyone was suitably protected, and no one was worried or confused that their level of protection was in some way inferior to the person that they were working with from another organisation in that same scene. And we also had quite a few interactions with members of the public who were I guess a combination of bemused, confused, and some individuals very, very worried. There was a lot of media attention on the incident, and also a lot of political pressure because of the nature of the individuals involved and the background to the incident. So there was quite a lot of stuff going on up here above and behind the operations that probably didn't actually influence what we did on the ground, but certainly put a lot of pressure from things like timescales and doing things far more quickly than we probably envisaged having had to do in the first place. And some of that we had to push back on and say, no, understand this needs to be done, but it needs to be done safely first and foremost, because if you cause harm to the people that are responding to this, you will run out of those people at some point very soon, and they will be no good to you. Plus, with the United Kingdom, we don't do that. We do our work safely and we do it properly. So there was quite a bit of pressure, that some of which had to be repelled somewhat. So just very finally, in the last minute or so, I've got the conclusions, I guess, to take from the talk today. The selection of respiratory protective equipment for use in emergencies and these crisis situations can be really, really complex. The equipment itself might be very, very simple, but deciding, understanding, assessing what the right piece of equipment and what the right approach is, it can be really difficult. And in order to support that and support those timescales, the risk assessments that inform and underpin, the use and how we interpret that hierarchy of controls that's been mentioned earlier, they have to be really, really flexible, and they will change. As I say, in my experience, almost on an hourly basis, but they will change rapidly. Don't be afraid of that. Just be prepared to work really hard on updating your risk assessments as things unfold. And it may well require zones within zones to be created. So you may have to be quite precise about what it is that you're worried about from a hazard point of view, and how you're going to actually protect and achieve your goals, achieve your objectives in quite a focused way, in quite a focused area. And you may need to start with very simple. So this is a bit of a contentious one, right? But we wouldn't normally do this, but you may need to start small and work your way up, and really use those hold points to make sure that you're not putting anyone at unnecessary risk. When individuals certainly from my organisation first arrived, there were some individuals who were, in some of the premises that didn't have a clue what was going on. As you wouldn't, the police had turned up, and then these weird people from AWE had turned up, and we needed to go and do some work to try and understand and start characterising the hazard. So to have turned up in the in the full suits with the things and the mouthpieces and the pipes and the tanks and so on would probably not have been appropriate, and probably would have caused more problems than it would have solved. And very much an attitude of doing what we can safely do, and do it now, rather than wait till we've got everything we need and all the information and all of the infrastructure behind us, because we'll probably be too late if we wait that long. And of course, the more complex your respiratory protection gets, the more complex the supporting infrastructure and the training burden and the operational footprint that you need to assign to it becomes. And that all takes time and effort and soaks up a lot of people. And people will generally be heroes and will want to work for longer and maybe harder and more strenuously than their protective equipment will really allow them to do. So you need to be really careful about that and keep an eye out for that, and make sure that it's not something that creeps in, and the people don't outperform the equipment, because that's a real risk. Okay, that's it from me. So many thanks for listening. Really appreciate the opportunity. I'll hand back to David. Thank you.
So thank you very much for that really insightful presentation, Paul. It's great to see the chat box. I know it's difficult when people are presenting, but we've achieved the aims of this society this afternoon. There's been a huge amount of discussion going on in the chat box, which is fantastic to see. In terms of questions, Paul, you've had quite a few. I'm just looking at the ones. I think the one I'd like to start with is from Lawrence, and it's going back to what you were just emphasizing about the hero point. And Lawrence has said, he's in the United States, he's saying certain authorities will argue that for a negative pressure respirator, you can work in excess of an hour. What are your thoughts on that in terms of kind of is obviously within the hero syndrome, people will just, I've done it myself in environments in the past where you think, yes, I can continue, I can continue, but then there's that safety element as well. Where are your thoughts around that?
I think, so if you agree beforehand that the task will enable, the physical exertion and the environment, the temperature and the heat and the other factors will enable you to work for longer than an hour, and your professional advisors say that that's okay, I don't think there's a problem. So I think, but you need to agree that before you go into a scene or a location. If you're starting to see people that should have been in there for an hour and it's now 50 minutes and they're just going to do another 2 or 3 things and get that bit done and so on, that's the time when I'd be concerned. So absolutely, I think there is flexibility there, and there are people far better qualified than me to actually specify those times. But it's just being mindful that should really be pre-planned and pre-agreed, rather than watching people start to fall over when we get.
Yeah, I guess it comes back to the risk assessment and how long, not how long you can wear the RPE, how long the task is going to take that you want to achieve.
Exactly.
And then you work from there. So, and then that brings us on to Patrick's question. Is there an accepted radioactivity turnback level for entry? In the US, it's typically twice the background level for first responders, unless there's a life at stake. Or do you think there's a more scalable or modular approach? Do we have standards, say, in the UK or elsewhere internationally?
So for internal radiation hazards, so things that you would wear respiratory protection against, it's very much case by case. It's very much done as an assessment at the time, depending on, you know, what the hazard is or what we understand about the hazard and so on. So those hold points could be very, very different. You might be in a really small confined space with a lot of material in it, or you might be in a massive, I don't know, a big warehouse that's got the same amount of material in it. So all of those considerations will affect your assessment on that. Where it's an external radiation hazard that's being presented, so we're not so worried about respiratory protection, but we're worried about protection from those external effects. There are a lot of the emergency service organisations in the UK will have a radiation dose policy, which will have certain limits, but they do differ a little bit because of what those organisations do. So the ambulance service have some figures that they work to, the fire service ditto, and the police ditto. For the police, it tends to be lower because the police tend not to be getting stuck into those hazardous environments in the same way. But again, those policies do vary a little bit across those organisations, which is, I guess, what I alluded to a little bit in my presentation there.
And so thank you for that. And then moving, so Harvey's asked, do all emergency wearers require PPE training prior to the incident? And again, I guess it depends at which level you're responding at.
Yeah, absolutely. I think part of the key to success with all of this stuff is using as many opportunities as you can to think through scenarios, work through scenarios, and then, you know, do some work, maybe tabletop, desktop type exercises to really think through some of these issues before they're there. The outcomes of that thinking and those conversations should then drive decisions on, you know, who we need to train to do what and how many people we think we need that maybe have a certain, you know, that are trained and ready, you know, and prepared to just go straight in with a certain level of protection. But it really is all about understanding and thinking through the scenarios up front for me. So, yeah, exactly how many and who, I think it comes back to do the risk assessment, understand the scenarios as best you can, learn from experience, right? So go back, look at these things that have happened in history and apply them to your particular problem set. Do some isomorphic learning. David will be sick of hearing me talk about isomorphic learning, but, you know, learn from other people's mistakes, and that should then help you to at least get a picture and a feel for how many people in your organisation might need to be trained to do what specific tasks with what levels of protection.
And then just thank you for that, Paul. Just one final one before we bring in Peter and Chris for the Ask the Expert, because there's, as I say, there's huge amounts of questions flowing in now, which is great to see. Paul, do you see a future for robotics in kind of CBRN, the malicious kind of support area?
So I see, obviously, the explosives ordnance kind of disposal community, so those that are dealing with potential explosive hazards are already big fans of robotics, and they use them. I think there's quite a bit of opportunity to integrate some of the radiological and other hazards, you know, detection and characterization equipment onto those robots, and maybe broaden their use case a little bit. In terms of some of the specific tasks that you would do, particularly in the kind of Litvinenko type situation, I think it's very difficult because the environments were so wide ranging that designing a robot, you know, or a suite of robots that can do all of the above is always going to be a challenge. But that said as well, I think that there's possibly, you know, I could think of other scenarios where certainly from a decontamination point of view, some remote means of automate, you know, some remote means of delivering decontamination agents and actually cleaning areas in a structured and a sort of automated way. I could certainly foresee some potential there. So I think there's definitely something there, but there'll always be, I think, as Peter alluded to, there'll always be a need for the human being, the Mark I eyeball.
Fantastic. So if we could bring Peter and Chris in, and again, this is a very timely one. Sean asked it quite a while ago, so apologies, it's taken us a while to get to to Sean to ask your question. And again, it brings in nicely kind of Peter and your presentations, Paul, in terms of how widely do controlled area definitions deviate across the industry. And again, with kind of a standard, what is considered nuclear industry, quite a controlled, regulated industry, as opposed to as you alluded to, Paul, it could be anywhere outdoors in a public environment. And do the controlled definition areas vary? I mean, my learning curve from today is hot versus extra hot. And again, anecdotally, but do you all work to the same controlled definitions in terms of exposure rates, or is it different for different agencies?
I can comment on that if that helps, David, as a start. From my experience, the sort of R and C categories are broad and consistent across the industry, the ones I've come across. There may be subtleties in terms of site-specific procedures, in terms of what that category is based on, but my experience is generally that sort of almost blanket rule that when you go from a C2 to a C3 area, you're into respiratory protection, tends to be consistent across the sites I've worked on, definitely in my experience.
Just because we like to be different to AWE, we actually have a slightly different, the basic principles are exactly the same. We used to use that system, but we actually stepped back from having the numerical values about 3-4 years ago, because generally our operations, we're quite fortunate in that we don't expect routine airborne contamination levels. So we do designate more on the potential for contamination rather than what's actually there. So if you actually go on what's actually present, all our areas are essentially the same because it's basically zero. But some areas have a huge potential if something goes wrong, and other areas have zero potential if something goes wrong. So we actually have a very slightly different system. And I think that's my experience. I broadly agree with Peter. I think that probably we are more of an outlier. But if there is a difference, it is the differentiation between sites that routinely see airborne contamination, who then designate on the actual levels they have there and then, versus the sites that have the potential, who therefore designate on the potential for it rather than what you would actually measure at that point in time.
Yeah, I absolutely agree with Chris. And I'd just add that what we try and do from an emergency response point of view is to apply the kind of industry good practice so far as we can. It's just more of a challenge. So, we wouldn't normally ask anyone to wear a level of PPE or RPE that wasn't commensurate with the hazard that we assess to be in that location. So it's exactly the same approach. It's just more complicated by those environmental factors that I alluded to earlier.
Thank you. One for Paul from an anonymous. How accurate do you consider the Litvinenko TV documentary "Hunting the KGB Killers"? Have you watched it?
I think I have, not for a few years now, but I remember it being a jolly entertaining watch. But I'd probably have to watch it again to give you a full and frank answer to that. I seem to remember that it was really more around the kind of investigative nature of the case, and the Litvinenko as an individual, and there was a little bit of science in there and so on. But yeah, so I'm probably not best placed to talk about in the widest context just how great it was. But I enjoyed it, and I'm sure, I'm sure the people that were practically involved, because there were, I think, a few people in that documentary who gave their kind of personal accounts of their involvement. Obviously, they were speaking from the best possible experience. So I'm sure their accounts were very, very accurate.
Fantastic. I'm just looking at the chat box, and I am interested as chair in the time. So I'm just turning my screen back on. I can't see any more questions. Just to give the presenters who've probably not seen, there's been a huge amount of really positive comments. Oh, sorry, one more question from Harvey. What is the minimum qualification requirement for face fitting and training of RPE in the UK? So I'm happy if you drop me an email, Harvey. I'm happy to send you information. It very much depends on the type of RPE, and that's enshrined in things like HSG 53 and INDG 479. So there's various government documents that outline those. So if you ping me an email, I'll be able to send you information on that. So
I can also, David, I can also just add to that when I wear the RPE, the beard has to go.
Yes, clean shaven at all times.
Clean shaven with respirators at all times. So yes, it changes day to day.
But with that, that concludes today's webinar. I hope everyone has enjoyed it. We've exceeded a record as a section. We've had 153 people attend, which is mainly due to the experts on the call that have given some excellent presentations. That concludes the 2021 program. We are looking for themes and ideas and volunteers for presenters for next year. We also have the ISRP International Virtual Conference in May, which if anybody's interested, look on the website. But if anybody's got any ideas or any burning desires to present, please drop myself or Mike, the secretary of the section, an email, and we're more than happy to look at ideas and bring you into the section. And with that, I would like to, on behalf of not just the ISRP, but also the Society for Radiological Protection, I would like to say a big virtual thank you to all three of our speakers today. I've thoroughly enjoyed it. I thought it was an excellent webinar. And with that, I would like to wish you all a pleasant evening and a very festive